Good. Appreciate it. All right, guys. Good to see you again. Let's keep talking a little bit. Last time that we were together, we did a substantial part of, we did a substantial portion of the old practice exam number 3, at least some of the highlights I wanted to do on that. There's some other things I wanted to do with the old practice exam number 3, and that then will carry over to the old final exam practice, and that'll get us through this whole thing. So I'm kind of combining the two a little bit. There's a few elements that I've not brought into play just yet. I'm going to do that. I'll do some more. We'll see. I mean, today I'll do a decent amount, and probably one more time I'll probably try to integrate a number of things together, guys. When there's this many problems, I mean, literally don't have them on me. I'm guessing somewhere in the ballpark of a total of 300 problems that could be done. I can't do all of them, guys. I mean, I can, but I think it would take so long. I don't know who's going to be able to even watch any of that. I try to watch. If there's 300 problems, I want to show you how to do every single one of those 300 problems by doing problems that are representative of those 300 problems. If there's 300 problems, you can do, I don't know, and you can do 40 of the most difficult. If you can do 30 of the most difficult of those 300 problems, 30 or 40 of the most difficult of those problems, and you can do them, then you can do all of them. If I can give you a representation of all 300 problems in just 30 or 40 problems, and you can do all of those problems that I gave you as a representation, and they're some of the more challenging problems as well, let's say, if you can do the most challenging problems, you can do all of the problems. That's always been kind of the way we look at stuff, at least the way I look at stuff when we do this. So there's a lot here. Let's kind of talk about this. They're asking you to sketch the graph of the quadratic functions below, given the vertex and axis of symmetry. Now they're saying a bunch of stuff here, guys. It's hard to know where to start because there's a lot there. Let me say a few things. Then let me hook around and do a few problems. And I think by the time I'm done, we'll pretty much have done everything that we need to do. For so much of what you need to know in the basic algebra that I want to train you on. If you know the basic algebra, you're in really good shape for a lot of different things. A lot of mathematics, a lot of extra mathematics, a lot of new mathematics that you want to learn. You do it with a foundation in algebra. You want to work in physics, you want to work in chemistry, you want to work in engineering. You start with a foundation in algebra oftentimes, and then you build your way up. So this is very important, folks. So let's take it really serious when we do this. Having said that, there's a number of things that come into play that are pretty useful to us. If you were, for example, graphing the function, let's say y equals f of x. So f of x equals x squared. So you're saying something like that. If you were graphing this, this is y equals x squared, period, end of the story. Something similar to that. What I'm showing you with the x squared function holds essentially for all functions in two-dimensional space. What I'm about to show you is going to hold for everything you see graphed in two-dimensional space, how things move around. This is crazy stuff, man, in its own way. I mean, in other words, somebody could say to you, okay, well, what if you change the function and you said the function was y equals x squared plus 4? Then it's 1, 2, 3, 4. This thing gets picked up. It looks like it's smaller, but it's not. That's just the base. If you move this thing down, it falls perfectly right onto this thing right here. And this is y equals x squared plus 4. This here is y equals x squared. What if they did this? Said minus 4, negative 1, negative 2, negative 3, negative 4. and this is y equals x squared minus 4. So this is y equals x squared minus 4, y equals x squared plus 4, and this is y equals x squared. There's a moral to the story here. If you're adding a negative number, you're dropping the graph down. If you're adding a positive number, you're picking the graph up. If you're not adding anything, the graph stays as is. Sounds good to me. Let's talk some more. Now, let's do it again. I mean, you got y equals x squared y equals x squared is that. Okay, we already said that over there. Well, let's talk. If you were to say y equals the quantity x minus 2 squared, that right there moves the 0 2 places to the right. 1, 2. It's a little odd. You thought, oh, it's going to go to the left, negative, but you got to minus it. If you go into the guts of the function, into the argument, you end up moving over. If you go into the argument of the function and you subtract 2 within the argument, you are moving the function over. If you subtract 2, you're moving the function over to the right 2 places. So watch out. If you add 2 to the argument, you move it to the left. It's a little counterintuitive, admittedly. That's this guy. Whereas this is that guy. Fascinating how that works out. So they're saying stuff of that nature. So if you go within the argument, they call for a function y equals f of x. This thing inside of the parentheses, they call it the argument. They say that's where you put the inputs in. From the input being put in there, it spits out an output. So if you go into the argument and add or subtract within the argument, you'll move left or right. Put another way, if you add a positive number inside the argument, you move to the left. Not up or down, you move to the left. If you add a positive number within the argument, you move to the left, like right here. If you add a negative number, like plus a negative 2, right? It's the same as saying plus a negative 2. If you add a negative number within the argument, you walk over to the right, not up or down. If you do multiplication or a function of a function or something like that inside the argument, other stuff happens. You tend to stretch out the function. You tend to stretch out what it looks like, or you tend to compress what it looks like. It's a pretty fascinating stuff in that regard. They're not really going there in the discussion that I have presented here for you, but it is a reality. If you do something within the argument, you tend to do stuff in the horizontal direction. If you were to multiply by a number within the argument, multiply by a number absolute value bigger than -1, I'm sorry, bigger than 1, a positive number bigger than 1, you are tending to compress the function, believe it or not. If you multiply by a fraction less than 1, still a positive number, you're tending to expand the function, believe it or not. Or at least you broaden it. So if you multiply by a positive number, a fraction less than 1, positive number, you tend to broaden the graph. If you multiply by a positive number bigger than 1, you tend to compress the graph. Things happen faster if you multiply by a positive number bigger than 1. Things happen slower if you multiply by a positive number less than 1. Positive number less than 1 multiplied inside of there will broaden the graph. It'll make things occur more slowly, so to speak. Whereas if you multiply by a positive number bigger than 1, it'll accelerate the process, make things work a little faster. They don't go into that too much, so I'm not either, but I am telling you that. Just something to have to kind of remember. But this they do talk about. This they do talk about, and we have it. They talk about various other things here. How do you act now? If they combine the two, what if they did that? What if they did this to you guys? And you'll see this in some of the work that you're doing. So I won't, I don't have to probably do it again. But if you started here, and this is y equals x squared. Let me see here. Okay, now we already know, that's y equals x squared. It's kind of our generic function that kind of acts as a surrogate, acts as an explanation to what goes on generally with all the functions. Okay. Y equals x squared is this. What would happen if you, well, y equals, I mean, there's a problem here, actually number, heck, I'll make it my own. Plus a negative, say plus a negative 5. They gave you this. How does that play out? All right, so let's see if we can erase that a little bit right here. That's a combination of the two. You got things going when you're adding on the outside. When you're adding on the outside of the function, let's see here. Let me just get this out of the way here, guys. All right, guys. You're taking this right here. And what's going on here? Well, you're adding on the outside of the function, so it's going to move things. If you're adding on the outside of the function, you're moving things up and down. If you're adding on the inside of the function, you're moving things east and west. So on the inside, things are going to go east and west. On the outside, they're going to go north and south. You got a combination of the two here. What happens is, on this side right here, you're making everything occur over to the left. 1, 2, 3, right there. Well, I'm not done yet. I just kind of drew it like that. And then add a negative 5, it goes negative 1, 2, 3, 4, 5. There's your answer. At the end of all that, here it is. You went 1, 2, 3, 1, 2, 3. You went 3 over, 1, 2, 3, and you went 5 down. 1, 2, 3, 4, 5. And I didn't draw this that well, but I want you to at least get the idea of what the heck's going on here, guys. What's the vertex? The vertex, first of all, there's an axis of symmetry. Goes right down the middle. That's not really part of the graph, but it just tells you it cuts right down the middle. And this is at x equals negative 3, comma, negative 5. X equals negative 3, y equals negative 5. And that's the vertex. Where does it intersect right here? Now, I just kind of, like I said, I drew this on the fly, and it's not necessarily, where does this thing intersect? Where it intersects, and I didn't even draw it that good, to be honest with you. The true intersection is, that's x equals 0. Put x equals 0 right here. X equals 0 minus 3 is negative 3. Negative 3 squared is 9. 9 plus a negative 5 is 4. Y equals 4. The y-intercept is 0, comma 4. Sure didn't draw this too good, guys, but basically, you know, assume I did. I mean, I don't, in reality, this thing should be looking, based on what we just did, right about here. That's where this is the better drawing. This right here is 0, comma 4 for a y-intercept. The vertex is negative 3, comma negative 5. This is y equals that's it. So this is the basic look to it, but look, I didn't really draw this that well. I mean, the y-intercept should be up here somewhere. It's a better look at it. But again, the argument, what's going on? What's the procedure? What's the procedure? You know, the procedure is what it is, guys. I mean, we're looking at it. You know how to go east and west. If something's going on within the argument, you're going east and west. If something's going on outside of the argument, so if you go into the guts of the function, you're going to go. If you go into the guts of the function, you're going to go east and west. In this case, you went west. So if you go into the guts of the function, you're going to deal with the vertical direction. If you go outside of the function, you're going to go north and south, up and down. Okay. So they talk about things of that nature. They talk about, you know, there's a couple things I want to throw in here. And again, this is kind of a hybrid, guys. It's got there's elements of there's elements of the practice of the old final exam in here, and there's elements of practice from the old exam number 3 in here. Who cares, guys? What I say at the very beginning of this whole process, who cares? The math is the math. Doesn't matter what language we're doing it in. Doesn't matter what book we're doing it from. If it's a good resource, we're going to work hard. We're going to know the math. It's as simple as that. So a lot of this stuff you're going to find in practice, in the final exam practice as well. Obviously, this stuff all is going to fall into the final exam practice as well. So I don't need to redo it in that regard. But there's some other stuff here we're going to do also. You see what else we can say here. Let's go into some of the conic sections. Circles, ellipses, hyperbolas. See how that all plays out. guys. Try to put this stuff together for you a little bit. You find different things in different textbooks. If you're talking about a circle, how's it going? All right, guys. So we're talking about a circle, you guys. This is a lot of ways you can play this, and you can see what emphasis is made. If the circle is centered at the origin, 0, 0, and the radius is r, the equation of a circle is x squared plus y squared equals r squared. Simple as that. End of the story. If the circle is centered elsewhere, right here, let's say this is the radius r, and it's h comma k, which h could be any real number, k could be any real number. The equation of the circle there is this. Look at something like this, and I say, okay, what's going on here? Well, it's not as hard as you think, guys. If you take h and you take k, if you take h and you take k and make h equal to 0 and k equal to 0, you're centering this whole thing at the origin. If h is equal to 0 and k is equal to 0, it becomes x squared plus y squared equals r squared. It's as simple as that. As simple as that. So that's talking about circles a little bit here. If you're talking about a thing called an ellipse, it's kind of a squashed up circle in a sense. And you know, different books give different talk about it, but let's put this in the A direction right here. We'll call this A comma 0 location. This is negative A comma 0. This is 0 comma B up here. And this is 0 comma negative B right here. X squared over A squared plus Y squared over B squared equals 1. If A and B are equal size, then the ellipse stretches in such a manner that it becomes a circle. If A and B are equal size, you can put A squared here, multiply by A squared, and you got X squared plus Y squared equals A squared. You got a circle again. That's some of the talk they're doing there. Sometimes the ellipse can have a look like this. And here we go, 0 comma B again. 0 comma negative B. A comma 0. Negative A comma, so I said I said negative a comma 0, a comma 0, 0 comma b, 0 comma negative b. Same thing. Holds up just like that. If you're to move this thing around, this works in either case, you guys. If you're to take this thing, and let's say move them around a little bit, there's things that happen. If you were to take this thing off center, I think it comes out like that. I'd have to look at it. I don't see here. I just got myself into something here. They're not really going there when they're emphasizing this. But since I entered, there's an old Greek saying, "Bikis to horo ta horepsis." If you enter the dance, you got to dance. So you got this. You got this. If you take this thing off center to there, it's 0 comma 0. Here it's h comma k. Yeah, it's gonna work out just fine. If that's gonna be the case, if you're looking at something like that, you took it off center, and this guy was 0 comma 0 right here, but you moved it. You moved it off center, and you're here. You moved it. You got here. Well, what do you got? Got x minus h or a squared y minus k. Yeah, I think it's gonna be fine. I think the way you move it, right? Where that would actually be, you guys. Let me see here. Let me make sure I got it. Let's talk about it a bit. They don't really go there too much, but you can. Let's say I started this thing. I might as well finish it off. If you're talking about this guy being 0 comma b, and this guy being 0 comma negative b, and this being a comma 0, and this being negative a comma 0, yeah, I mean it'll manifest itself. It'll manifest itself. Sure, it'll work that way. To make this whole thing work. For example, if you'd have been here, if you'd have been right here, this would have been over that way, and the a would be a different a. The a would be as big as negative a minus h. That's how big it would be actually. So it works fine. Here it's not as far over, but when you subtract this, you get the distance between them in that direction. Here the distance between them should be straight on, should be fine. Okay, so you're looking at something like this. And that's about ellipses, you guys. We got a thing called the hyperbola. And it's interesting because what we were dealing with, without, I don't know to what level I want to take this, you guys, given the volume of work that we're trying to do. But earlier when I had the y equals x squared, that was an example of a thing called a parabola. Parabola, from the Greek word para, means over or next to. Bola is from voli, which means shot or something thrown. Something fired, something shot, something thrown. Paravoli means it's thrown somewhat quite far. Hyperbola is from the Greek word hyper. That's where hyper comes from. Hyper and voli is a shot as well. Hypervoli. Hyper means super shot even more than a parabola is. Now, what does that mean? Probably want to erase, I think. Let me erase here. Let's go there. Let's start a clean slate on that one. See how you can talk about it a little bit. Okay. Let's just talk about a hyperbola. I told you to. Hyper is the Greek equivalent of the Latin super. Super in Latin, hyper in Greek. If it wasn't for Greek and Latin, there's not a whole lot of English. Or at least there's still a lot. English is a beautiful language, but English is a beautiful language. One of the reasons it's such a powerful and beautiful language. One of the reasons is it's borrowed heavily from Greek and Latin, quite a bit. Anyway, so we got hyperbola. What's that all about? Hyperbola. All right. Well, hyperbola's got the attribute of doing something like this. Here's a point. Here's a point. Let's say this is 0, comma b. This is 0, comma. Now the different books write different things, you guys. I don't have a specific textbook in front of me. As I'm saying this, as I'm writing this, I'm going to get more orientation down the road. For those of you at my MATC class, I'm getting more orientation down the road in about a week on how they're exactly doing this. So I don't, regarding what book is there or not, that's neither here nor there. I'm sure it's a great book and it doesn't really matter the language that's being used and how they're approaching it. So just kind of be aware of that. I'm going to see some other stuff here in a second. That's a negative b right here. And I don't know, let's see here, I'll go right here. And then it kind of fires out like this. And it doesn't fire out, it kind of looks like a parabola, and yet it's not. It's more radically firing out to do that. And that's the graph of it, period. And they got these made up lines that they put here, and they call them asymptotes. Goes that way, that goes that way, that goes that way. And we got to talk about that. Now, these aren't part of, these red things, the red things that I just drew are not part of the graph, but they do give you kind of boundaries as to how the graph behaves. The black lines that I drew are the graph. The red lines, the drawing here in black is the graph. What is in red is kind of like the asymptotes, how this thing actually plays out. Let's talk on this. Like I said, I don't have a textbook in front of me, guys, so I don't want to give you a bunch of garbage here. We got this right here. We got y squared over b squared minus x squared over a squared equals 1. At x equals 0, 0 divided by a squared is 0. At y equals b, b squared over b squared is 1. 1 minus 0, that'd be this point right here. So it kind of gives you an idea what's happening here. They have got a way to do so. I don't know if I want to go down this path that I'm about to go down, but let me go there anyway. You could solve for y, sort of. It's not really a function because it doesn't pass the vertical line test. Later on, when you get into functions, you guys, a function, y equals f of x, a function is something, if something goes like even this, if you draw a vertical line, it can intersect at most 1 point. It cannot intersect at more than 2 points and be called a function. So a function, if I draw a vertical line, bam, it intersects here. Bam, it intersects here. Bam, it intersects here again, which is the same value as this, but that's okay. The vertical line test tells us that that's a function. Vertical line test tells us that that's a function. If such, so that's a function. This is not a function, because when you draw a vertical line, it's intersecting at more. It's intersecting at more than one point. If anywhere this thing intersects at more than one point, it's not a function. So this guy's a function. This guy's not a function. All right, guys, I don't know how legible that is. Hopefully, it's not a function on this one. So this guy, not, give myself a little more room. Function. Not a function. Because it's not passing the vertical line test. And we'll get more into that. A function is one-to-one if it passes both the vertical and the horizontal line test. Well, this is a function, but it's not a one-to-one function, because if I draw a horizontal line, it intersects at multiple places. That's not a one-to-one function. Nor is and nor is this. I mean, it would pass the horizontal line test, but not the vertical line test. So these are not one-to-one. This is a function that's not a function, and neither one of them, though, however, is a one-to-one function. A one-to-one function would be a function that, let's say, did something like this. This thing passes the vertical line test, because it's only intersecting at one point, and it also passes the horizontal line test, because it only intersects at one point. Only intersects at one point. Over here, it only intersects. So all horizontal lines intersect at just one point at most, and all vertical lines intersect at just one point at most. All horizontal lines intersecting at most one point, and all vertical lines intersecting at most one point means this is a one-to-one function. All right, guys. I'm sorry I had to digress, because later on we're going to need to know that. When we do some of these things, only for something like this can you get a thing called an inverse function. Can you go back and forth? I got a function, now I want to go backwards and get back to where I started. The thing that'll do that, in the strictest sense, you need the function to be a one-to-one function. The reason I said that, guys, is this right here is not a function. Why? Because if you draw vertical lines, they intersect at more than one point. It's not a function. However, we can pretend it's a function if we get rid of the bottom thing here, or if we get rid of the top thing here and just leave one of them. Then it behaves like a function. Forgive me. That's why I needed to digress a little bit and tell you what a function is, what's not a function, not a function, and a one-to-one function where vertical and horizontal line tests are passed. It'll come useful to us later. So I figure I just might as well, you guys got the camera, you can always go back and look at what I just said. So in some regard, at least we're capturing everything, and it's not lost. You can always just go back and look at what I just said regarding functions, not functions, and one-to-one functions. These lines right here are of what form? Tell you what I'm going to do. I told you it's not a function. You can't pass the vertical line test. But let me solve for y anyway. Let me add a positive x squared over a squared on each side, and then multiply by b squared on each side. Y squared would equal x squared over a squared x squared over a squared plus 1 multiplied by b squared. Y squared equals b squared over a squared times x squared plus b squared. If you square root both sides, you square root both sides, y is plus or minus the square root of b squared over a squared times x squared plus b squared. Now, if x is a really, really big number, this is huge compared to b squared. The square root of it approximates, the square root of the square root of b squared over a squared. If you get really, really big values of x, or really big values of negative x, a big absolute value of x squared is huge. Huge times a number is still huge, plus a moderately sized number. If this is really huge and this is moderately sized, the square root of this quantity is roughly the square root of just this. The square root of b squared over a squared x squared is b over a times x. Y equals plus or minus b over a times x. That's what these guys are, guys. That's what this is. This is on the positive side. Okay, I don't like the way the mark. I tell you that the mark. Here, let's try it again here. Y equals yes, true. In this case, note to self, don't use the blue marker. I'm going to have a hard time erasing that one, right? Maybe not. There we go. Should be all right. Be careful with this, guys. This is plus. This is minus. As you go toward infinity, as you go toward negative infinity in the x direction, as x goes toward negative infinity, or x goes toward positive infinity, these guys get closer and closer together but never touch. They never touch. This is always going to be a little bit bigger because there's a plus b squared here. It's always going to be above. It's always going to be above those lines. It's going to be always a little bit above them, but it's going to get closer and closer to it. On the downside, on the negative side, it's always going to be more negative. It's always going to be more down than this is over here. Same kind of thing going on. Pretty fascinating stuff. They call those asymptotes. They asymptotically approach one another. The graph asymptotically approaches these two linear, the graphs of these two linear equations. Y equals negative b over a and y equals positive b over a. So that's interesting. A good way to remember that is the b is associated with the y, the a is associated with the x, the rise over the run is change in y over change in x. This is associated with delta y. This is associated with delta x. Delta y, delta x, I guess b would be on top of a. B would be on top of a. Good way to remember it. Good way to remember that. And again, there's other stuff you could say. In fact, let's please say it. Let's go like a little bit different direction on this one, if you don't mind. Okay, so all right, guys, these pockets are something else. I get my stuff on here. What if the situation was add up a little bit more here. All right, what if this was the case? Let's leave the A associated with the X and the B associated with the Y. Let's see how that plays out. Let's see exactly how we want to play this thing. And let's say that we're writing this. Again, this thing does not shoot out like a parabola. It hyper shoots out substantially more than that. So this is what if it's doing that? Well, guys, here we go again. There we go, drawing those lines again. Those lines are not part of the graph, but they are the asymptotes. I wonder how this plays out. This is how, I guess there's a moral to the story here, guys. If the y values are in the lead and you're subtracting the x values, if the y values are in the lead, they open up in the y direction. You know, like stereo speakers, I guess you could say. The stereo speakers open up in the y direction if y is in the lead. The hyperbola, the two major portions of the hyperbola open up, the two speakers open up in the y direction if y is in front. The two major portions of the hyperbola open up in the x direction. The speakers open up in the x direction if the x is in front. Okay? So, let's see what we can say here, guys. Let me play some games with this again. Let me add a positive y squared over b squared on each side and subtract 1 on each side. It becomes y squared over b squared. Let me add a positive y squared over b squared on each side, and then subtract 1. Let's multiply by b on each side. By b squared on each side, rather. I think you know where I'm going, guys. Well, look at that. You still got b squared. You still have b squared over a squared, x squared, b squared over a squared, x squared. Square root each side. B squared over a squared, x squared minus b squared. Now what's going on? Now what's going on is the same thing that was going on earlier. If the value of x has a very big absolute value, if the value of x has a very big absolute value, then if you square it, it's huge. You multiply here, huge. Huge minus relatively small is still huge. The square root of it for very big values is approximately equal to the square root of the quantity b squared over a squared x squared, which is the square root of the quantity b squared The square root of the quantity, b squared over a squared x squared is that right there. So here we go again, plus or minus y is equal. It's the same thing, guys. It's the same thing, yet a little different. This is on the small side. This is smaller. This right here is smaller. Smaller. I mean, I don't want to erase this, but I could erase this right here and make this greater than on the plus side, and whatever. There's a lot going on here. In terms of absolute value, this is smaller than b over a times x. Smaller, huh? Yeah. Look at it. It's underneath. This asymptotically approaches this. It's always. This thing is always right here, because this is that's where this came from. Right here, this, right here. Came from this. Most significantly, it came from this. I mean, they all came from each other. This right here goes here, it's that, okay, whatever. If you square root this, it's going to be a value that's smaller. Let's forget the positive and the negative can mess us up, I guess. Let's get rid of positive and negative. Let's just talk about the positive side. Get rid of this, get rid of this. The square root of this, not counting plus or minus, the square root of this is a smaller quantity than this. Get rid of that, get rid of that. The square root of all this is a smaller value than this. Absolutely. And you can see it's a smaller value. Right here, smaller. This is below him, means smaller. The black line, the black drawing here is less than the red drawing. The black drawing here is less than the red drawing. So smaller that way. Here, however, it's bigger. It's not as negative. If you put it on the negative side, the square root of this is a negative number that's not as negative as this number. The absolute value of this is bigger than the absolute value of that. Always. So what does that mean? That's a very important thing. If we're talking like you got rid of this and got rid of this, the absolute value of this is always bigger than the absolute value of that. What does that mean? That means on the plus side, it's more plus, and on the negative side, it's more negative. And here you go again. And there you go again. And you got y equals plus b over a times x. And this is negative b over a times x, as far as the asymptotic lines are concerned. And that's the hyperbola. There's a lot there. I mean, there's a good amount there, you guys. Not that bad. I mean, it's not, and again, just go through the screen, go through the film, a couple times if you want to. It's pretty fascinating stuff, the way the whole thing plays out. All right. I'm skipping some minor, down the road, there's some other stuff. I'm skipping a little bit of the minor points. I'm trying to hit all the major points when we do this stuff. So I think we're looking pretty good when we do it. When we read the material and stuff, I think we're going to be in pretty good shape to do this. The way they got this whole thing set up for us, and third's going to be very reasonable. I'll try to be as reasonable as I can be as well, you guys. I understand that the best way to teach is person to person. There's nothing better. There's nothing that substitutes for that. I said that a long time ago. Before that was maybe even fashionable, I guess. That was always my philosophy. I think I feel almost vindicated. You hear it on television. The best thing for students when they're face to face, person to person with people. Of course, that's always been the case. Okay, let's see what we got here. me get this out of the way for you. We'll talk about some more stuff right now. I talk about the logarithmic function, the exponential and logarithmic function. Let's see what we can say regarding that. All right. There's a good amount that can get said regarding a lot of this stuff, you guys, regarding the logarithmic and exponential functions. Now, we've already talked about some things that I'm going to hook around and talk about again. We talked about, it's important enough, I think we got to just talk about it quite a bit. If somebody were to say to you, x to the m over n, and I don't want to get into all the details of how you can play this. Let's say m and n are positive integers, and they can be anything, any positive integers. If you want to make them negative, I already told you about the negative, how you can do negatives, how you can do positives, how you can do rational numbers. All rational numbers, or forgive me, every irrational number could be approximated by an integer. As closely as you want me to approximate it, I can approximate any irrational number can be approximated to any degree of accuracy that you would like. Wouldn't be exactly equal to it, but you could get it to any degree of accuracy that you would like through rational numbers. X equals this. And we said a lot of stuff. We said you can write it like this. We also said you could take it and say, put the 1 over n here. That'd be the nth root of x, the whole thing taken to the end. Doesn't matter, they're equal though. They're equal. Well, they got this thing called the exponential. It's sort of, they kind of go hand in hand, I guess you could say. They've got the logarithmic and exponential function. And it's hard to kind of call it. I mean, you could say a bunch of stuff here. Let's talk a bit, if I could. If I took, just trying to think of a good way to actually put this, I guess. If I took, let's say, x, and then I got its nth root. I started with x, guys. Okay? I started with x, I took its nth root, and then I took it to the nth power. That gets me back to x. If I started with x, and then went to the nth power first, and then got the nth root, did this backwards, still got x. What are we talking about? If I did the number 3, and I took the number 3, right? Let's just mess with it here, I guess. Take the number 3 and I take it to the 4th power, I get 81. Okay. True. It is 81. I took 3, took it to the 4th power, and then I took the 4th root of 3 to the 4th. Sorry, here's this cleaning fluid actually works fantastically, but You gotta kind of be careful, you gotta dry it up a bit too. The fourth root of 3 to the fourth is 3. What if you took this? You took 3 and you got the fourth root first. Do it on your calculator. Get a 1 point something. Then take it to the fourth, get back to 3. It doesn't matter if you do one and then the other, you still get back to where you started. It doesn't matter if you do one or the other, as long as you do them both. Let me go back here. Doesn't matter which one of the two that you do first. If you do one and then the other, it doesn't matter which one you do first and which one you do second. As long as you do both, if you do one and then the other, regardless of the order, you always get back to where you started. Functions that behave that way are one-to-one functions, and they are inverse functions of one another. An inverse function gets you back to where you started. An inverse function gets you back to where you started. So I'm kind of going in a roundabout way. I said I was going to talk about logarithms and exponents. To do that, you almost got to talk about inverse functions in a sense. If I said to you, y was equal to 3x plus 5. There's the function, f of x. You know, y equals f of x. If it's a one-to-one function, and it is, if you graph this, it's a straight line. So all vertical lines intersect at only one place. And all horizontal lines intersect at only one place. It passes the vertical line test, and it passes the horizontal line test. That's a one-to-one function. It should have an inverse function. This function right here, y equals f of x, should have a function known as the inverse function. Be careful with that. I'll tell you what that means and what it doesn't mean. When they say this, the inverse function of x, ladies and gentlemen, that does not mean this. Don't ever write that. Does not mean that. If you wanted to write what I just wrote, you'd have to be talking about this thing right here, the whole quantity taken to the 1 power. That's 1 over f of x. Correct, I would agree with that. This is mathematically valid. This is not. This is symbolism for inverse function. The inverse function gets you back to where you started. Give an example. We already kind of gave an example. Let's do another one, I guess you could say. Start with the number 2. Forgive me, easier one maybe. Start with the number 4. What do you say you take the number 4, square it, and then square root it? You get back to 4. 4 squared is 16. The square root of 16 is 4. What do you say instead of squaring it first and then square rooting it, what do you say you square root it first? The square root of 4 is 2, and then square it. That's also equal to 4. Whether you take 4 and square it first and then square root it to get 4, or whether you take 4 and square root it for, here I took 4, squared it first, then square rooted and got 4. Here I took 4 and square rooted it first and then squared it, still get 4. If you do one then the other, you get back to where you started. What's going on here? What happened down here, you guys, what happened up here? Basically, y equals x squared and y equals the square root of x are inverse functions of each other. If you take a number and square it and then square root it, you get back to where you started. Or if you take a number and square root it first and then square the result, you get back to where you started. That's what I mean. Take the number 5. Take the number 16. Take the number, put x equals 16. Take the number 16. 16 squared is 256. Take the answer, 256, put it here, square root 256, you get back to 16. Or take 16, square root 16, get 4, take 4 and square it, you still get 16. Whether I take 16 and square it, whether I take 16 and square it and get 256, take the 256, square root it and get 16, or take the 4 here, square root it, take the 16 here, square root it, get 4, and then take 4 here, square it, you get 16. If I do one, then the other, I get back to where you started. These two guys are inverses of one another. If y equals x squared is a function, y equals the square root of x, these are inverse functions of one another. These are inverse functions of one another. Same thing here. What did we do here? Let's say you had y equals x to the 4th and y equals the 4th root of x. That's really what was happening here, guys. I disguised it, but it's true nevertheless. It's true nevertheless. For example, let's put, I don't know if I want to do this, but let's do it anyway. Let's put 81 right here. 81 to the 4th power is 81 times 81 times 81 times 81. This is really big. It's in the millions. Between, it's probably somewhere on the order of 40 million. 81 to the 4th power. Take 81 to the 4th power and put it right here. What's 81 to the 4th power, the 4th root of it? What number times itself 4 times will give you 81 to the 4th power, which is 81 times itself 4 times? 81. The 4th root of 81 to the 4th power is 81. Now go the other way. Put 81 in here first. What's the 4th root of 81? It's 3. Put a 3 up here. 3 to the 4th power is 81. These are inverse functions of one another. Just like these are inverse functions of one another. And this is where I'm about to find the inverse function of this one. A lot here. So let me see here. Let me see exactly where I want to. All right, see what we got. We just said something here. I mean, let's look at this guy up here. There's some attributes of these inverse functions. Here's one of them. Let's take just the right-hand side of x squared. It looks something like that. This is y equals x squared. Let's take the square root of x function. It looks something like this. I know there's this guy that goes this way. I know there's this guy that goes this way. That wouldn't be a function. It's called a relation. If it's not a function, it's called a relation. That's neither here nor there for us. What's going on here? All inverse functions have the property that each inverse function has the exact same size and shape as the other inverse function, as its inverse. Each one is the inverse of the other, and both functions are the exact same size and shape. They're just located in different places. If you were to pick up y equals x squared, pick him up and spin him around what? If you're to pick him up If you were to take this guy right here and spin him about this line that's at a 45-degree angle associated with this little box right here, if you were to spin him this way, he'll fall right onto him perfectly. No more, no less. If you were to take the bottom guy and spin him upward, he'll fall right onto him. They're the exact same size and shape. They are mirror reflections of one another about the line y equals x. About the line y equals x, they're mirror reflections of one another. Had it here, this is not a road I want to go. This is a very similar graph to y equals x squared, and the other guy is real similar that way. This is y equals x to the fourth. This is y equals the fourth root of x. This is y equals x. It's the same exact thing in this instance. Inverse functions have that attribute. They are the exact same. It's hard to talk about size when these are infinitely big. So I'm not being very rigorous when I tell you that. I think you're going to let me get away with it. Just say, look, for a given snapshot, if you want to just draw them proportionally and cut it anywhere you want to cut it, they are the exact same size and shape. They are the exact same size and shape. A better way to put it is they are the exact same curve. Each of them is the exact same curve. They're just located in different places. And if you rotate one, if you rotate one the right way, you get the other. If you rotate the other, then you get the first one that you were talking about. If you rotate one, you get the other the right way. They are mirror reflections of one another about the line y equals x. Inverse functions have that attribute. Inverse functions have the attribute that they are mirror reflections of one another about the y equals x axis, no matter what they look like. You know, if one of them looks like this, the other one's going to look like that, and then it's going to do this. They're still mirror reflections of one another, et cetera, et cetera. Very important. If you do one, then the other, you get back to where you started. Well, if I wanted to plug in the value of 10 right here for x, for this guy, y equals 3x plus 5, plug in a 10 right here. 10 times 3 is 30, plus 5 is 35. Now I got to take the answer, 35, and plug it into the inverse, and it'll come back and say 10. Well, I got to find that inverse function. Is there a way to find the inverse function? Yeah, there is. There's a lot of ways to look at it. I'll give you one way. I'll give you kind of like two looks at it, and I'll give you kind of the easy way to look at it and get the right answer. Okay? What we got here?